Okay, so welcome back. So the first effect is multipaction effect. It's a resonance type phenomena. So to understand this phenomena, let us consider a parallel plate system. We can represent a rectangular waveguide, its top and bottom plane by this parallel plate. Some electromagnetic signal it's propagating through this parallel plate. If I consider any time instant, let us say at that time instant the top plane it is at positive potential compared to the bottom plane, and somehow there is an electron present inside these two planes, and we are considering a vacuum scenario. That means we do not have any air particle or any dielectric in between these two plates, only the electron is present. So according to field direction, electron it will be attracted to higher potential or positive plane, and it will gain kinetic energy. If this energy is sufficient and it is more than that required for secondary emission from this plate, then while it will strike this top plane, it will generate 2 electrons. So this second one is due to the secondary emission. So for that, electron should have sufficient kinetic energy. Now let us say when the instant when this second electron is generated, at that point the electric field it changes its direction. Now what will happen? Both of these 2 electrons they will be accelerated to bottom plane. So again they will gain kinetic energy from the applied electromagnetic field, and if they have sufficient kinetic energy, they while striking the bottom plane it will create more electron. So suddenly there is an avalanche of electrons. So but to do that we should have exact phase relationship. That means when this electron just reaches this first plane, exactly at that instant it should change the phase between these two plates, otherwise electrons won't be accelerated towards bottom plane. So that's why we called it a resonance phenomena. Without this phase relationship it won't happen. So as a result of this, we have suddenly many electrons which conducts energy between these two planes, and we have an effect of breakdown. So it's very prominent with the device which is inside is vacuum. For example, in particle accelerators or for any component waveguide based components, particularly air filled rectangular waveguide based components, when we use for space application where we do not have any air. If we use some air or dielectric material inside, then it will disturb this electron trajectory and we won't have multipaction phenomena. So multipaction is mainly prominent for the vacuum case. Now how to predict multipaction, or what is the threshold voltage needed for multipaction? It's really difficult to calculate the multipaction threshold voltage, because it depends on many factors. It depends on type of metal, because the secondary emission threshold energy needed for secondary emission, it depends on type of metal, surface of metal, and presence of any other molecule inside the rectangular waveguide structure. So instead what people does, they use a chart. This chart is given by European Space Agency. They did some experiment for different types of metal and for different gaps between two plates and for different voltage values, and they produced this chart. This is from the measured data. It shows peak voltage across the gap along y axis, and along x axis it is frequency gap product. This is interesting. it not only depends on frequency, but also a function of the gap between two plates, and the unit here it is gigahertz millimeter. So, frequency is being measured in gigahertz and the gap between two plates it is in millimeter, and we see the multifaction phenomena it is more prominent at lower value of f into d. So, for a given device, if the gap compared to its lambda is very small, then multifaction probability it increases. How to read this data? We have several curves for different types of metal. For example, they considered aluminum, copper, silver, gold, allodine. So, for aluminum this is the graph, this is the plot. Then we have for the copper, and right side we have two different slopes. For this A region slope is given as 40 for aluminum, for this B region it is given as 27, and for the A region it varies at C into F into D, and for the B region it is actually F into D square. So, we call the right side part of this curve is safe region where multifaction will not occur, and left side you can see one more plot, one more line here. So, in between this left and right line, this zone is susceptible to multifaction, that most probably multifaction will happen, and left side of this line where we can say for sure multifaction will happen. So, we have to avoid these two regions. So, here is one example, fabrication example. This is a band pass filter designed in rectangular waveguide technology. So, most probably you can identify this is a cutter view. We have many cavities inside. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 cavities inside. It is a 10 pole band pass filter, and on top of a broad side wall you can see there are many screws. So, these screws are used to adjust the coupling and as well as the operating frequency, and inside we have air. So, when it will be sent to any orbit where we do not have air, so inside will have vacuum. So, before sending to space we have to go through this multifaction test. We have to first see is there any multifaction effect or not. So, this type of structure is very prone to multifaction. Why? Because of this screw and because of the cavity, you see there are many metal plates inside. So, the D separation, effective separation, it decreases, and the multifaction probability it increases. Next one is ionization breakdown. Sometimes also we call it corona discharge. In this case, we are considering another scenario where air is present inside rectangular waveguide. If we have dry air, usually we do not face any problem, but if we have water vapor inside, we have a problem. So, how this breakdown occurs? This is due to ionized molecules, and water vapor it is very easy to ionized. So, let us say the electric field which is applied between top plane and bottom plane, it is sufficient to ionize the molecule. You can compare the effect with Zener breakdown and avalanche breakdown of any p-n junction. So, here the electric field value is so high that it can tear out electrons from the molecules, and that is how the molecules become ionized. So, the main condition is that the electric field should be higher than a threshold value, and that threshold value it depends on again the shape of metal surface, what material you have inside, what is the pressure of the gas, whatever you are using inside, what is the frequency of operation. So, what is the distance. So, there are so many factors, and again it is really difficult to calculate the actual value, but here at least we have one closed form expression for threshold electric field. So, let us see. So, air ionization threshold field EP RMS value, it is given by this expression. This is a closed form expression. So, we have the parameter P, which represents air pressure. P is equal to P naught into 273 by 273 plus T naught, where T naught is the temperature in degree centigrade and P naught is the air pressure in torr. Omega, this is the operating frequency, angular frequency, and we have some other factors like L effective. L effective represents the diffusion length in centimeter, and tau p, it is the pulse length in second. So, if you look at the expression, if I send a pulse through rectangular waveguide, it will have some duration. Tau p is the duration of the pulse. So, if I increase tau p value, what will happen? EP will decrease. So, ionization breakdown, it can occur at much lower electric field value. So, we have a curve here for the threshold electric field value versus pressure plot. This is called Paschen curve for pulsed microwave breakdown in air for different L effective values. L effective, it changes with, of course, pressure. So, L effective, this is L effective, it depends on the type of molecules or the type of gas inside. L effective, we are considering three values here, 0.01 centimeter to 1 centimeter, and now we are considering it for two different pulses. For one case, tau p is 10 nanosecond, and in the second case, pulse width is 10 microsecond. So, as we expected from the previous expression, for longer pulse, threshold electric field, it decreases. So, if we have any electric field above this, then for sure ionization breakdown will occur. And one more thing, ionization breakdown, it is a localized phenomena, because we have gas molecule inside, and usually the mean free path of air, it is smaller than most of the physical dimension. So, that is why it is a localized phenomena. Now, let us consider one interesting thing. Let us say we are testing a waveguide bandpass filter, and it is designed in rectangular waveguide technology. Now, ionization breakdown may happen or multifaction breakdown may happen. So, from the structure under test, how do we understand which breakdown occurs first? So, once a breakdown happened, after that we open the structure and then look at the burning mark. If it is in small region and dark, that then it is due to ionization breakdown, and if it spreads over a longer area, larger area, and the marking is usually faint, in that case it is due to multifaction breakdown. So, looking at the burning mark, then you can decide this is due to ionization breakdown or this is due to multifaction breakdown. So, next, how then we can improve power handling capability for any rectangular waveguide based structure? First, when we are designing prototype, we have to use larger bandwidth if possible. What is the advantage of larger bandwidth? Then we can spread our energy over different frequencies. So, it will decrease the threshold electric field value, it will decrease the electric field value. We have to use symmetric design if possible. Then physical design consideration, if we have small gap, then obviously electric field value increases. So, if possible, we have to use larger gaps. If we have smaller gap, which we can't avoid, then in that case we can fill up those gaps by using some solid dielectric material. So, solid dielectric material, it will not allow ionization breakdown or multipaction breakdown. Then avoid sharp edges, use rounded corners, it will avoid ionization breakdown, use proper venting design, then some external control, employ inert gas under high pressure, but remember it should be avoid of any water vapor. Then use DC or magnetic biasing to disturb electron trajectory and destroy resonance condition. So, what is the advantage of that? Multipaction, we have seen it's a resonance phenomena. So, if we can disturb the electron trajectory, most probably we can avoid multipaction breakdown. Then apply a very thin coating that has a low maximum secondary electron emission yield. So, that is how we can increase this threshold voltage for multipaction breakdown, and then finally take care of contamination. So, after this rectangular waveguide, next we will start the printed lines. So, among the printed lines, most popular even at millimeter wave frequencies are microstrip line and CPW line. For microstrip line and CPW line, what we expect that loss alpha value will be much more compared to rectangular waveguide. And then what is the use of microstrip and CPW line? The main advantage is its low profile structure, its fabrication is much easier and it is cheaper. So, obviously, if we use microstrip line, it won't be long, we will use mainly for chip to chip connection or as interconnects. So, keeping this point in mind, so let us first discuss then what are the basic characteristics of a microstrip line and what are the different sources for a sources of losses for a microstrip line. So, if I go back, this first figure, it shows a cross section of a microstrip line. So, we have a top strip, metallic strip, it sits on a dielectric layer and below we have a ground plane. This is the plot of electric field and magnetic field. Most of the electromagnetic energy, it is confined inside the dielectric, and below this strip we have some fringing fields in air. So, this is a semi open structure. So, keep in mind that we can't place any other structure like packaging wall near the central strip. When you have any other metallic structure, you have to maintain some separation between that structure and the central strip, otherwise there will be power coupling and it will change the characteristics of microstrip line. Microstrip line, it supports quasi TEM mode, it is not exactly transverse electromagnetic because of these fringing fields, because we are dealing with two different epsilon r values. So, epsilon r inside it is that of the dielectric material and outside epsilon r is equal to 1, it is of air. So, because of that we call it quasi TEM, but since most of the electromagnetic energy is confined inside dielectric, so the properties of microstrip line is mainly determined by the dielectric constant of the dielectric slab. Let us consider, to simplify the analysis, this strip, it is inside one effective dielectric material surrounded by this effective dielectric material, for which we are defining some effective dielectric constant epsilon E. So, its value obviously will be more than air, and it will be less than epsilon r, since it is the effective epsilon E. Then we have a closed form expression for epsilon E. Epsilon E, this is equal to epsilon r plus 1 by 2 plus this factor. You see, it is a function of the dielectric thickness and also a function of the strip width W. The characteristics impedance of the microstrip line Z naught for W by D less than equal to 1, you can use this first formula. So, if you know thickness of the dielectric, width of the strip and the effective epsilon E, then we can calculate Z naught from this expression, and when W by D is more than 1, we use the second closed form expression. So, what we see from both of this expression, for a given thickness, if we increase W, then what will happen? Characteristics impedance will decrease. For a given W, if I increase thickness, then what will happen? So, if I characteristics impedance will increase. So, in this case, then for a given characteristics impedance, we can choose W value for a given substrate material, because substrate for a given substrate D is fixed. For usual microwave or millimeter wave system, always we deal with 50 ohm characteristics impedance. It is always 50 ohm if unspecified. For very low frequency applications like coaxial cables used for television, the characteristics impedance we use is 75 ohm, but for microwave and millimeter we use 50 ohm. So, there is a reason for that. If I calculate the minimum attenuation for an air filled coaxial cable, attenuation is minimum when the characteristics impedance is approximately 75 ohm, but power handling capability is maximum when the characteristics impedance is approximately 30 ohm. So, we use 50 ohm, it is somewhat in between 30 and 75 ohm, and it is a standard value used everywhere. So, now once we have epsilon E, we can calculate phase velocity Vp. This is C by root of epsilon E. Now, epsilon E is always more than 1. That means, Vp is always less than C. So, microstrip line, it supports slow wave mode, not fast wave. We have closed form expression for attenuation constant due to dielectric loss alpha d. This is a function of epsilon r tan delta as well as frequency, because we have a term k naught here. So, as frequency increases, then alpha d also increases. And the attenuation constant due to conductor loss alpha c, it is surface resistance divided by Z naught into W. So, if I increase frequency, RS will increase, obviously alpha c will increase. So, that means at millimeter wave frequencies, we see that alpha d and alpha c both will increase. Not only that, in addition to these two different sources of losses, we also have surface wave loss, and we have seen the detrimental effect of TM0 mode, and always there will be TM0 mode excitation. So, power will be lost to TM0 mode. Now, we can keep TM0 mode excitation to a minimum value only if the height or thickness of the substrate is much smaller compared to lambda g, typically 1 by 100 times. So, which is not possible at millimeter wave frequencies. So, at millimeter wave frequency, typically if I keep on increasing frequencies, then the thickness of the substrate, it will also increase with respect to lambda g. So, in that case, surface wave excitation will increase and surface wave loss will increase, and it is a problem not only at millimeter, even at higher microwave frequencies also. So, if we fabricate anything in PCB technology, whatever loss we are expecting from this expression, so that is not enough. We also have to consider surface wave, and the structure it becomes very lossy. That is why we can't use a microstrip line or a CPW line for long distance transmission. We only use for interconnects or for chip to chip connection. So, some other parameters, some approximate values, lambda g, this is equal to lambda naught by square root of epsilon re, this is beta 2 pi by lambda g, and theta is equal to beta L. Since we are assuming it as TEM mode, we can use the formula whatever we learned for a 2-way transmission line. So, in next we will see there are some other factors which determine highest frequency of operation, just like the coaxial cable. We have to avoid surface wave mode generation to some extent. We have to avoid any higher order TE mode or TM mode generation. So, from these conditions we have some high frequency limitations of microstrip line. Thank you.